Hello everyone, I am Sandeep. I am here to talk about Cartesian product and relations. Let us give me a abstract of this presentation. We define the Cartesian products and the nth Cartesian power subsets. An n array relation, an array relation on set is subset of nth Cartesian power. We study the most common properties of binary relations as reflexivity, transitivity, and various kinds of symmetrics and antisymmetries. Via these properties, we define equivalence, partial order, and preorders. Finally, we describe the connection between equivalence and partitions of the given set. Let us understand about the Cartesian product and relations. A Cartesian product M cross M2 up to uh, Mn of set M1, M2 up to Mn is a set of all n tuples satisfying M belongs to M for all I in the set of n elements. The Cartesian product of n copies of a single set M is called an nth Cartesian power. We denote the nth Cartesian power of M by M power n. In particular, M power 1 equals M and M naught is the one element set which is also called null set. An n-ary relation on set M is a subset of M power n. Thus, unary relations correspond to the subset of M. Binary relations to subset of M square equals M cross M, etc. Let us understand about binary relations. As defined above, a binary relation is a binary relation on a set M is a subset of Cartesian power M square equals M cross M. Given such a relation, say R is a subset of M cross M, we will usually use the notation A relates to B for A comma B which belongs to R and A comma B belongs to M. Let us list some important properties of binary relations. By means of them, we define the most common classes of binary relations, namely equivalence, partial orders, and quasi-orders. A binary relation R on set M is said to be reflexive if A, A relates to A for all M belongs to M, and transitive if A relates to B and B relates to C. If A then A relates to C for all A comma B, C belongs to M. If it is symmetric if A relates to B, then B relates to A for all A comma B belongs to M. It is antisymmetric if A relates to B and B relates to A, then A equals B for all A comma B equals M. A comma B belongs to M. And it is asymmetric if A relates to B if negation of B relates to A for all A comma B belongs to M. Now we are ready to define the above mentioned important class of binary relation. An equivalence on a set M is a binary relation on M that is reflexive, transitive, and symmetric. A partial order on M is a reflexive, transitive, and symmetric relation on M, while a strict or partial order is a transitive and asymmetric relation on M. Another important class of binary relation is the smallest class containing all equivalence and orders. By definition, a quasi-order is a reflexive and transitive binary relation. Let us understand about equivalence and partitions. Let E be an equivalence relation on a set M. The block of an element A belongs to M is a set. It is given below. Before understanding the structure of blocks of an equivalence relation, we define a partition of a set M to be a collection P of pairwise disjoint subsets of M such that it is a such that subset of P equals M. Let us study one lemma 1.3. Let E be an equivalence on a set M for every A comma B belongs to M. A equals B if and only if A is a subset of A intersection B. is not equal to null. Proof: it is clear that A equals B, then A intersection B is not a null. In order to prove the opposite implication, assume that A intersection B is not equal to null, then we can pick C which belongs to A intersection B for every D belongs to A. We have D equivalence A equivalence C, and C equivalence B due to symmetry. Applying transitivity of E, we conclude that D equivalence B, which says that D belongs to B, thus A is subset of B. The opposite inclusion is proved similarly. It readily follows from lemma that the block of an equivalence relation on set M form a partition of M. Indeed, it follows that the block are pairwise distinct and as A belongs to A due to the reflexivity. Their union is the entire M. Such a partition will be called the partition induced by equivalence E. On the other hand, a partition P of a set M gives rise to the relation say E, defined by A equivalence B if and only if A and B belongs to the same block of P. It is straightforward to verify that E is a reflexive, transitive, symmetric. Moreover, the partition P consists of the blocks of E. The outcome of this discussion shall be the observation that equivalence relations on a set M correspond to partitions of M. Let us understand about orders and quasi-orders. First, observe that every partial order on set M corresponds to unique strict order on M. Indeed, given an order R on a set M, the binary relation it is given below is a strict order. Conversely, given a strict order S on the set M, the relation R is defined by A relates to R if and only if A subset B or B is strictly defined A is a corresponding partial order. Let us show that a quasi-order on set M decomposes into an equivalence relation on M and an order relation on the corresponding partition. Let Q be a quasi-order on M. We denote by E the binary relation defined by A equivalence B if and only if A, A is a quasi-order of B and B is a quasi-order of A. Let us understand lemma 1.4. The relation E is an equivalence on M. Let us understand the proof of it. Since Q is a reflexive, E is reflexive as well. Suppose that A equivalence B and B equivalence C for some A comma B comma C belongs to M. Then A quasi order B and B quasi order C, whence A quasi order C due to the transitivity of Q. The symmetry of Q implies that B quasi orders A and C quasi orders B, and so C quasi orders A. Since both A quasi orders C and C quasi orders A, we conclude that A is equivalence C. This proves that E is transitive. Symmetry of E is seen readily from its definition. These guarantee that E is an equivalence on M. Let P denotes the partition of set M induced by the equivalence relation E. Let us continue with the lemma 1.5. Let A equivalence A dash and B equivalence B dash for some A dash B B dash belongs to M. Then A quasi orders B if and only if A dash quasi orders B dash. Let us understand the proof. Suppose that A quasi orders B from A equivalence A dash, we have that A dash quasi orders A, and from B equivalence B dash, we infer that B quasi orders B dash. The transitivity of Q implies that A dash quasi orders B. The opposite implication is proven similarly. Let us understand with the lemma 1.6. The relation R on P is reflexive, transitive, and antisymmetric. That is, it is a partial order on P. And the proof of it, the reflexivity and transitivity of R follows readily from the reflexivity and transitivity of Q. In order to prove that R is symmetric, suppose that for some A comma B belongs to M, A relates to B and B relates to A, it follows from the definition of R that A classifies B and B classifies A, which means that A equivalents B. Therefore, A equals B. This proves that the relation R is antisymmetric. Thank you.